Hey there, everyone. Thanks for joining us. I'm Yotam Azriel. I'm founder and CEO at Tensorleap. Tensorleap builds applied explainability platform to help AI teams to debug, monitor, and curate datasets, everything to get safely to production. We are at the first webinar today as part of a series of webinars. We're going to cover different kind of topics from data curation, domain adaptation, explainability, and production monitoring for neural networks. Today's session is going to focus on concept attribution, explainability, and how we can actually understand the kind of representation our model managed to learn, especially in vision different tasks. Today's webinar will be led by Thomas Fel. Thomas Fel has extensive work and research around concept attribution and explainability. I saw him for the first time in the last ICCV. It was a brilliant talk. I'm very honored to host you today. Thank you so much for joining us. I'm going to hand it over to you so you can give us a brief introduction on the subject and yourself, and we can get started.
Thank you very much, Yotam, and thanks again. I mean, super honored to be here today for this webinar. Also for inaugurating this new Tensorleap series of talks. So really briefly today, I'm going to try to talk about kind of the talk I gave at ICCV, which is about the idea of reflecting on interpretability and more precisely interpretability in vision, and how the field has been driven mostly by method, so pushing new method on top of each other. And really few work have tried to make the effort of trying to understand why some of those methods works. And now it's starting to change. A lot of work has been appearing in the literature now trying to shed light onto like why some method works, why some of them doesn't work, which lead to this more complete picture of like what I would call a phenomenology, so a study of the phenomena that we've been observing in this deep vision model. And that's what I'm going to try to talk about today. So this kind of shift between method-driven and phenomenology-driven. Really quickly about me, so I'm a researcher at Harvard University. I done my Ph.D. in vision interpretability at Brown University with Thomas Fel. And before joining Harvard, I was at Google working with Catherine Harman. All of those years, I was working in vision interpretability or around vision interpretability. Also worked a little bit on complexity and training deep vision models. And so really quickly today, I'm going to focus on the interpretability side. And I'm going to give a three-part presentation. First, really a quick introduction on interpretability and interpretability in vision. I will focus on what I think is one of the most interesting area of research right now, concept extraction, and why I think the linear representation hypothesis is probably one of the most exciting discovery of the last 5 years in interpretability, and try to explain why I think not the method, not the sparse autoencoder that you may have heard of, or the method are important, but the underlying hypotheses are important, because I think some of the methods start working, and I think it means that some of the assumption we are making kind of makes sense right now. And I will finish by questioning whether they are complete, now whether the job is finished or not. And if we are here today, it's probably because it's not finished. And so I'm going to try to give you a sense of what I mean when I say like maybe the representation assumption are incomplete. I wouldn't be here today if we didn't have this big problem. It's called the black box problem. Right now, AI system, a big AI model, including vision model, are trained on billions of data with a specific recipe that we call a learning algorithm. And once this model is trained, they're able to make superhuman prediction. And the problem is this system is absurdly complex. And when I mean absurdly complex, I mean it's literally this. So here, for example, is a single heat maps. So a single grid of 16 by 16 token activation, okay, that is hidden among one of many channels of a single neural network. And this single channel is in fact hidden in the single little blocks, in a single little component of a single blocks. This blocks is just, again, one blocks of an entire series of layers. And this result is just for one single image. Oops, sorry. So this is what I mean when I mean black box. It's like those systems are extremely complex, and to try and to understand them, we need to invent new method and new technique to try to simplify and have an actionable ways on those models. So what does the researcher have done? Well, one of the first method and the first waves, I'd say, of method were what we call attribution methods. Methods are really famous now. They started with Zeller and all, and was this so-called silency maps, and they evolved like more complex, more heavy also in terms of compute attributions method, like RISE, for example, as you can see on the right. And the idea is we had a plethora of methods that have been developed. And the reason we have this plethora of methods that have been developed is because the definition of attribution method is kind of vague. An attribution method, or to have those heat maps that tell you where the model look, you need to implicitly define what you mean by importance. And there is not just one way to define importance. There is an infinitely many ways to define importance because we are projecting this high dimensional function to like a single scalar to tell if a variable is important or not. And so projection into this higher dimensional space, so this lower one, there's an infinite number of functional that does that. So there is many definition of importance. Maybe you heard about Shapley values, which start from axiom and try to build a method that respect those axioms. Sobol and this is also are doing so, integrated gradient, and so on and so forth. And all of them, deep inside each method, is a different kind of definition of what they mean by importance. And so after this kind of long pursuit into which method is the best, with the invention of some metrics along the way, some researcher asked like whether those methods are actually useful to understand what's going on inside our complex vision systems. And in one work that we've done with some of my colleagues, notably Julien Collin, what we've done before is like just take three simple use cases of explainability and try to see how well a human can understand what's going on, how well a human can understand what the model will do on a new input by observing a lot of input and a lot of heat maps. I will spend more time on the concept, so I will not go into too much detail, but basically what we found in this really small experiment on thousands of humans across 6 months is that on simple cases, attribution are useful, and they are able to reveal the most important part of what the model is doing. However, in more complex and realistic cases, only looking at attribution is often not enough. And human can understand part of the system, but usually a lot of the juicy, interesting phenomena are not really captured by those methods. And so there was a series of papers was arriving at the same time, and on to not few of them, the one from Peter Haas, the one from Sunny Kim, from Nguyen, and of course also some paper that really discarded or at least found really strong limits in attribution, notably the one from Julius Adebayo and Ben Kim. And the consensus at the time was that attribution are useful, and in elementary context, they reveal enough information to understand most of the system. However, in realistic use cases, this is not enough. And they only give us where the model look, so where in the image, but it doesn't tell us what the model is really looking. So when it look at, for example, the head of a fox, what exactly is the model seeing? Is it the color? Is it a particular texture? Is it a particular shape? Or is it something else? So this distinction from where to what is at some point drive the field toward the second part of this talk, which is dedicated to spend more time on the concept extraction of neural network. So of course, if we want to understand the concept that the model has, the first idea could be, let's just study every neuron. And this is how it started. So people start studying what each neuron reacts to. And in fact, we have a fixed number of neurons. So if we understand all of them, maybe we can understand all the system. However, we quickly realized something that is interesting and not new, in fact, because it's well known by neuroscientists, which is called a distributed representation. What I mean by that is like we found that the model are storing concept or useful recurring patterns, not in a specific neurons, but between different neurons, and use the high dimensional aspect of their activation function to store many more features than the number of neurons. I will go into detail a little bit after. Basically, what it started with is people realizing that those neurons were polysemantic, so they were reacting to many different aspects at the same time. And so to overcome this thing, to overcome the fact that we don't have access to the basis the model is operating on, like the neuron is not the correct basis the model is operating on, a series of methods appeared, and one of them we developed was named Craft. The idea was extremely simple. You take a lot of images and you send those images into your neural net. Once you send them into your neural net, you have a packet of activation. So a lot of activation, let's say activation coming from rabbits. And we are going to name those activation A. It's a big matrix, n by d. And the idea is to do data mining on those matrix. So in particular, we're going to do like a matrix factorization. So the idea is to recover this matrix A by two positive matrices, Z and D. And if you understand the meaning of those matrices, what they mean, basically, the interpretation of those matrices, then you basically understand everything you have to know on concept extraction. So the idea is the following. This matrix A of activation going to be factorized into two matrices, Z and D. Z represent for each input which concept has been found, and D represent a collection of atoms, a collection of recurring patterns, a collection of concepts. And of course, we don't know a priori which concept will be. So we learn at the same time and the new bases and the new coefficients in these new bases. And by solving this optimization problem, we recover a potential basis that the model is operating on, which is different from the neuron basis. And then once we have solved this optimization problem, we go back to something more useful and tractable. We have concepts, so we can watch them, we can see where they activate, how important they are, and where in the particular image they can be found. So for example, here for the rabbit, the model has apparently three different concepts: the head of the rabbit ears, and the fur of the rabbit. And that leads us to this kind of result where for a given, for example, model says run at 50 on the class Chenso, we can automatically discover for example, here the model is telling us I'm using six concepts to classify Chenso, and those concepts are the head of the Chenso guy, the genes, the motor, the blade, the trunk, and the trees. And we can, after that, study how important they are by just making fluctuation on this concept space to see which one really drive the model decisions. And for example, here we have the motor and the blade, which seems to be driving most of the logits, so most of the decision of the model. Of course, we can do cool thing with those concept bases. Here, for example, is a case where we were able to automatically identify and try to understand the failure cases. So here you have on the left the concept found for the lemon. So here to classify lemon, the model is using 4 different concepts over there. And on the right, you have all images that are not lemon, but are classified as lemon. So there are like hallucination of lemons on the image. By looking at which concept exactly the model is using, we can have a sense of like why the model is getting wrong. For example, here for the orange peel and the peel texture of this on this image, maybe the reason the model is like answering lemon. Or here over there, you can see on the roof of a church, the model is answering lemon because of the lemon wedge shape that you can see over there.
Thomas, in your framework, is there any way to measure or to get some kind of understanding towards the ability of this concept to generalize, or how specific is that concept?
Yeah, there is, in fact, didn't have a lot of time to present that, but usually I have another slide that go a little bit more into detail on that topic. I think it's the concept basis may be incredibly useful, especially for that. So to answer this question about concept statistics, and we study in this paper 2 things, which we call prevalence and reliability. So I don't know if they answered perfectly your question, but the idea was the following. Is there some concepts that are specific from some classes, or some concepts that are shared across different classes? And also, is there some concepts that are more reliable in terms of decision? So for example, when I classify lemon using this strategy or this other strategy, is there some difference in the kind of reliability of my model in that case? And we found both to be actually true. There are some concepts that are really specific to some classes and some others are shared, and the reliability is not linked with the prevalence, which is a bit weird because it's not really Bayesian way of thinking. It's like some strategy maybe are rare and not really common, but extremely reliable. For example, for the coffee, we have this latte art coffee patterns that we can sometimes see. In the data set, there are not a huge time there's not a lot of image that contain this kind of latte art. However, the reliability is really high. It means that every time the concept is here, the probability of being right is nearly around 100%.
Mm-hmm.
So yeah, there's definitely more to dig into with those statistics of like concept prevalence and concept reliability and this kind of stuff.
Right. Interesting. And did you manage even to get to a numeric metrics that is like encapsulate how specific is the concept, or just rule of thumbs that help us to understand how robust this concept?
Yeah. In fact, so two metrics that you can develop pretty easily from this thing is when you have the matrix, so the Z. So the matrix is telling you, the Z matrix telling you which concept activate on which board. And so by studying the statistics of this matrix, you can do two things. One is just a simple average, which tell you how often a concept fires. And the second one is, because it's positive and sparse, second one is a conditional energetic measure. It's like you take a subset, let's say, for example, on a given class, and you check the energy for a given class, depending on the energy on the entire data set. And so by marginalizing like this, you can have a sense of how specific a concept is. If you want to test some particular hypothesis about like, is this class specific, or is it that data set specific, or is it any other, anytime you can basically define a boundary between two distributions, then you can have a sense of like specificity. Okay. And so basically to come back to this method, this concept extraction method, at the time, like a series of works start appearing nearly at the same time. And so I presented you Craft really quickly, but there was ACE from Gormani and Kim. And more recently, maybe you heard about sparse autoencoder and recent shift of Entropic towards this kind of method. And so at that time, we started to wonder, like take a step back and wonder like two questions. First, among all the methods that have been invented, is there some common underlying principle to this method? And second question is, if they make some assumption, then what assumption do they make? And do they share any assumption? Is there some shared assumption between those methods? So for the first question was, among all the methods that has been invented, so ACE, ECE, Craft, and other, is there a global pattern? Is there some global framework until which we can put them under? And found out to be true, and this a good candidate is dictionary learning. It's a really old field in applied math and linked to compressed sensing. The idea is the following. Again, we have this big packet of activation, and we want to find these two matrices, Z and D, that recover the matrices, the big packet of activation, okay? And by putting different constraints on those matrices, we recover all the method that has been invented at the time. For example, really quickly, if for each Z, we oblige Z to be extremely sparse, just one somewhere and zero elsewhere, then we find the k-means. Or if we oblige the dictionary to be completely orthogonal, then we find like PCA or SVD. If we oblige like the Z and D to be sparse and positive on both sides, you can recover Craft. And for the SAE, you have a really small linear network, so just one layer linear network that give you, and you want a sparse Z. So that's all. It's like it's extremely simple. All the method could be recasted as dictionary learning with different constraints. And in fact, one could argue that those constraints make implicit assumption about what we mean about concept. Think about it like k-means. The interpretation of k-means in our case, the concept are centroids. It's pretty simple. However, for Craft, NMF, and SAE, it's become a little bit more complex. The interpretation is slightly different. And in fact, we can even go into, I don't want to spend too much time, but even go into too much detail and say like, even the projection operator, the sparsity of projection operator that use in different sparse autoencoder themselves make assumption about the geometry or the underlying geometry that we seek or that needs to be here for the SAE to work, for example. Okay, so let's go back to this. So is there any underlying principle that govern many of the methods that have been invented from concept extraction? Yes, dictionary learning. And second question, if there is like this common framework and this common big idea between all those methods, is there such thing as like a common assumption? And this is probably the most important slide of the talk. So if there is one moment to focus, it's now. I'm gonna try to be as easy as possible. What I will argue here is that probably, in my opinion, the biggest discovery of the last 5 years in vision interpretability has not been the method, but the underlying assumption of those methods that we have converged to. Basically, the methods that have been invented have been slowly converging into making similar assumption, and I'll try to write it down here. as clearly as they can. So this underlying assumption, often named like linear representation hypothesis or LRH, states the following thing. It's like we are operating in the space, okay? So the space of our activation space of our neural network. And we say that this space respects LRH if there is three conditions. First, the number of features in that space is larger than the number of neurons. The model is able to pack way more feature than the number of neurons. Those features are packed in a way that is like as orthogonal as possible. So we cannot be perfectly orthogonal. In the space of dimension D, you can only put D feature in a perfectly orthogonal manner. So if you want to put more, they're gonna have a small interference. It's called thus the quasi-orthogonality. And then finally, those features, the price you have to pay to pack more feature than number of neurons is that they can no longer activate all at the same time. So they have to have a few number of features that activate at the same time. But the thing you gain from having this kind of implicit sparsity is like now you can pack way more feature than number of neurons. So why we have that and what's become a phenomenology, because we have a geometric characterization. Here I just state what the geometry look like. And then I can even give a motivation. Say this geometry look like this because of this compression argument. It's the way for the model to pack and to compress way more feature than the number of neurons. In fact, the Johnson-de-Strauss lemma, which often is applied in the other way, in the other direction, basically tell you approximately you can pack exponential D feature in the space of dimension T. I'll let you imagine if you're operating in a space of 1000 dimension, how much feature this model can potentially have. And so basically it looks like this. We have a geometry, for example, here in 2D, and if you try to solve this problem, it gives you this kind of thing where, again, the features are not necessarily aligned with the neuron, which is what we observe generally, and they are packing way more feature than the number of dimensions. And the funny thing is, if we assume LRH, if we assume the linear representation hypothesis, then dictionary learning is the perfect dual of this assumption. It's like it is the method to recover the concept if we assume that the concepts are like this. And this is where I was trying to tell you that this thing is like the method slowly converging also means that the assumption is slowly converging and the assumption is answering the method. Little fun fact, yes. Yeah.
It's a very nice perspective on, why small neural networks might generalize better.
Tell me more.
So the conversion of, so you have much more features that has to converge to less concept, and less concept need to generalize towards more. So sometimes, just working with neural networks many times, we have this feeling, at least, 10 years ago, this neural network is too big. We're gonna memorize everything. We're gonna
you're right.
Yeah. Everything. But when you force the model to centralize features into a specific concept, you're gonna force it to generalize, which is just another way to say the same thing, right? It's another.
Absolutely, yeah. The compression, of course, if you diminish the dimensionality. In fact, the bound that I just show here is it's not the real bound that we want. It's probably more something that compressed sensing. It's more complex, so I didn't put it here. But the compressed sensing bound is a little bit more restrict, and it may intervene the factor K, of the sparsity over there. So if all the features fire at the same time, you can pack even less. So there seems to be an interplay between, as you said, the size of the neural net and also how much feature activate at the same time. Like there is a tension between those two factors that create the space that we are seeing.
Mm-hmm. Nice.
And the funny thing is like the geometry I just described is a pervasive geometry that appear in many ways in natural science. So for example, I'm going to give like really quick example. On the left, you have what we call the Thames problem. The pore in the pollen, they are called like aperture. They are the site where the pollen tubes emerge during the fertilization. And for the grain to germinate efficiently, the exit point must be well spaced. And so in nature, we observe this kind of geometry on pollen apertures. In physics, maybe you already know, but there is this really famous Thomson problems. Like the idea is we want to minimize the electrostatic charge to minimize the Coulomb energy. And so basically the adjustment of those electrons, like also the exact same geometry that I just described. And finally, closer to us today, the signal processing, there is something called the spherical code. The idea is you want to design a configuration of point on the sphere that enables robust resistant encoding. So when you have two people discussing with small channel and they want to communicate, you have to solve the exact same problem. And funnily enough, there is an old paper from Claude Shannon that if you look closely at this paper, like already having the Welsh bound and some other related measure that are extremely linked to this problem in 1958. So all those geometries, pervasive things, in fact, have the same mathematical substrates, and these mathematical substrates are called Grassmannian frame, and they are really well studied in mathematics and applied math. And so this Grassmannian frame is the optimal configuration, given a dimension and given a number of points, how to put them in a more angular way on the sphere. Okay, so we took a step back and basically asked two questions: many method, one common principle, dictionary learning, and all those methods have some kind of common assumption, and it seems that the linear representation hypothesis seems to be one of the, at least one of the assumption that the most, if not all the methods are implicitly making to some degree. Okay, so with this assumption and with this method, we can again instantiate sparse autoencoder, NMF, or any other concept extraction method that you want, and already answer pretty cool question. So I'm gonna shamelessly show some of the work that we've been doing. One was 2 years ago with Kat and Arman at Google, where we studied the complexity, so how complex and easy feature occur during the training. And what we found using, again, this phenomenology was that we found what we call the sedimentation hypothesis. We found that the feature, the way the model learns this feature is like it's compressing in a sedimentation process. The feature are like getting stored earlier and earlier inside the neural net. So for example, if you have an important feature like the eyes of a dog, then when you start the learning, the eyes of the dog feature will be at the last layer, and slowly during the training, it will be pushed as early as possible, and at the end of the training, maybe you will have the eyes of the dog at the layer 15 or the layer 10 or closer to the input, basically. So the model is like trying to do this kind of sedimentation process where you push the important feature to be available as early as possible. Another work that we've done is called like universal sparse autoencoder, where we try to find a common concept space between all different vision model and found like the concepts that are unique to some model and also the concepts that are shared across different models. Another work that we just finished with Matthias Boacek is where we use like sparse autoencoder to basically understand what a generative model can and cannot generate. So we use a diffusion model and we detect all the concepts. So we talked about it just before, but the statistics of the concept, the prevalence of the concept, the specificity of the concept. And we found that some different model cannot generate some concepts, some blind spot. There are some blind spots in a completely unsupervised way. We just throw out like 30,000 concepts and inspect the distribution of each one of them. And when there is a huge difference, we can go and inspect what it is and discover some blind spot of our favorite diffusion model. And finally, I'm going to go really quickly into some recent work that we've been doing on DynoV2, which is an excellent vision model developed by MEFA and Timothée Narcé and Maxime Cab. So basically, here you have 32,000 concepts, okay, in DynoV2, and I'm coloring them depending on whether they are used to solve different tasks. So on the left, they are colored in yellow if some concepts are used for classification, in blue if they are used for segmentation, and purple if they are used for depth estimation. It seemed that first, the model is like recruiting or like leveraging different concepts to solve different tasks. And then when we zoom into those different tasks, what we see is pretty interesting. First, for the classification, I don't want to spend too much time on it, but what we found is the model has developed a weird way of solving the task, which is using the real concept we would expect. Like, for example, for the rabbit is using the true like rabbit mask, a mask around the rabbit and a rabbit concept. But the other concept is using in conjunction something that we call the elsewhere concept. So again, it's a little bit complex, but let me try to explain. The idea is what we found for every single object and every single animal that we inspected, there is a concept that fires exclusively outside of the object, okay? But when you remove the object, this concept disappears. It's basically the model way of like slowly putting the information about there is a rabbit in all the other token except the token where there is the actual rabbit. So it's like a token that's basically a concept that signifies there is a rabbit, but it's not here. There is a rabbit in this image, but it's not here. It's in another token. That's for the classification. For the segmentation, it seems that the model is largely relying on contour and ownership boundary. And all those contour-based concepts form a low-dimensional manifold that we also characterize in the original paper. And for the depth estimation, the model is leveraging 3 different kind of depth Q, monocular depth Q, that are also known for human, because humans are able, even with a one eye, so monocular depth Q, to estimate the depth, and they use, it's well known in neuroscience, like different Qs. At least we know at least 5 of them, and 3 of them are partially here in Dino. So one of them is like local frequency transition. So when you have bokeh effect, as you can see over there. One other is like projective depth. So like trying to spot lines and curves. And of course, the line and the curve in the real world will not be straight in the back of your retina, but making the assumption that the line are straight inform you about the geometry of your ambient space. And finally, the shadows. So the model has a lot of shadows detector that allow him to understand a little bit more the geometry of the space.
Right.
Any question?
Well, first of all, it's brilliant. It's just brilliant. And the presentation is brilliant. Just out of curiosity, do you guys manage to come up with a technique to detect anti-concept or missing concept? So for example, if you mispredict and you don't predict just because, partial of the object is occluded, is there any techniques in your framework that you're familiar with you can detect and measure the impact in case the concept will appear?
So yeah, as I was telling you before, I think it's like extremely relevant, and those are actually questions that I'm passionate about and that I'm trying to solve right now. Okay, so one idea, just like that, is if we have enough data point, the statistics of the concept, especially the statistics of the co-occurrence concept. When you have the matrix Z, okay, you can just do the Z transpose Z. So it gives you the matrix of co-occurrence. So for example, it will tell you often with a coffee, you have the cup and the handle of the cup, and then the coffee inside. So you can basically recover some kind of graph that tells you usually those things appear together, okay? So you have some kind of implicit graph hidden inside your matrix Z. When you have this graph and you have a new data point, you can basically estimate how probable, this new input is according to this graph. Because the graph you have is secretly a data generating process. It basically secretly telling you P of Z, the probability of drawing a specific Z from a distributions. So I would say that that's probably one direction that I think is promising to solve that. I don't know if it's the good one, but I think the question is really good. Actually, I think that's one of the questions I'm super interested about lately. And about like proper anti-concept, I don't know for that, but I suspect Dino has such thing, especially with the healthware. We found that there is some kind of weird negation going on in those feature space. And I don't think we've discovered the basic of it, but I think there is much more to do on that topic. Yeah, I agree with you.
Maybe you know what? One more question before I interrupt again. In the case of domain gaps, many times different companies need to deploy their AI platforms to different kind of domains, and autonomous vehicles will drive through different cities and different weather. And Amazon Robotics gonna have a bunch of different kind of products coming in and different warehouses. And the problem of domain gap, domain adaptation is super challenging. And from what we hear now is it's mainly detecting concepts that contributing to the model to perform better. But do you think there is a way to utilize the framework in order to better understand the kind of concept that created a certain kind of domain gap in the model perspective?
That's also another good question. Yeah. How would you do that? Do you have any intuition?
I would consider to try to find maybe the centroids of those different clusters of concepts and try to subtract the main concept that's leading from one cluster to another and detect some kind of vector trajectories to detect the kind of the main concept that differentiate between the different kind of environment. Maybe if we'll be able to split and characterize different kind of concept that's related to movement, concept that's related to object, concept that's related to background, we'll be able to come in and give some extra information about different kind of domain gaps and their impact.
Absolutely, yeah. I think that's a good, that would be a good track. I mean, yeah, maybe another one could be like study it at the distribution level. So like imagining like the data set and model plus concept as like a push forward function, and you send your entire data set as a push forward, and you have a measure on the concept space, and you can again like split new domain and old domain and have two push forward measure. I mean the same push forward measure but under two distribution. And studying the shift in the distribution and the concept level can also like give you in that regard like potentially some insight also on for this kind of question. But yeah, I think that's an open question too. I mean, that's super interesting stuff. Maybe to finish, and this is the technical slide, so don't worry if you don't necessarily get it entirely. The main message of that is after studying the solution found by those method to extract concept, what we realize is we are far from the idealized way of linear representation hypothesis. So here, I don't know if you remember, I talked to you about the Grassmannian thing. So the optimal packing, you can think of it as the optimal packing of feature that would have this signature, the signature of the green thing over there. And the red thing is when we initialize our dictionary, when we initialize our method, the signature, the spectral signature of our method is the red one. And so one would expect that we go from the red to the green. So the blue line would be in between, trying to reach this perfect case. And in fact, we found the opposite. So the model, the solution found to discover this concept is not really related. It's like going in the other direction as our assumptions, which suggests that it's not the end of the story, that the optimal packing, that there is more to just the optimal packing in the neural net. And in fact, there is a movement right now in the literature. So after the first wave of method that were the saliency map and the first wave of problem, we have this second wave of method, or the concept-based method, and we start to have the same way, a second wave of problem. And those problems are, for example, the dark matter of SAE, which basically states you can enlarge, make your dictionary as large as you want, and there is still a portion of the activation that you cannot fit, that are not that cannot be predicted by those linearly. And the part that is missing is actually important. Jonathan Belinkov was telling me that the others, I think it's absolutely right. It's like the part that is missing is not noise because it's important for solving the task. Another problem is instability, which is something we studied last year in the archetypal sparse autoencoder paper, where we found that those concept method, when you train them on Monday and you train them on Tuesday, exact same data, exact same seed. I mean, sorry, just the seed is changing. You found completely different concept. So that means that we may have an infinite number of solutions to the problem we are trying to solve. And that leads me to this more general issue of identifiability. When we try to solve the problem I was showing you before, finding the basis that recovers partially the activation, we have huge potential of having identifiability problem. I really encourage you to look at Locatello's work. He's been working on that since a long time now. And the problem would be we may have an infinite number of bijection, an infinite number of solutions to that problem. And so which one is the correct one? And the theorem of Locatello and their friend and their colleagues basically show that if you have this kind of identifiability problem, as we have right now, one solution to that problem is like finding a good inductive biases, finding a way to nudge into the good direction. And then finally, lately, a lot of paper, and there is one every day lately, on finding like some geometry that are absolutely not linear inside neural net. So they are hierarchical, non-linear. They form like beautiful patterns, and it's in that the model are like way more complex than just packing linear features. Finally, something that would be interested in lately is steering, and we also found that those concept-based methods are recover concept, that those concepts cannot always be found useful in terms of steering, and in fact sometimes they don't even work at all. And all those problems lead us to reflect on like what is going on and what is actually missing. So the field is actually having this kind of question about like whether what is actually missing. And what I heard is that potentially the problem is not coming from the method, but the problem is coming from the assumption that we are making. What are the assumptions that we are making right now is the LRH, and what is the one we should be making? And what structure remain invisible when we use the method and implement and instantiate those linear representation hypotheses. And some of us, not the only one, have this kind of secret agenda, like this secret roadmap for interpretability, where in 3-step, where we believe that if we find a good basis, if we extract the correct concept, and we are able to characterize the operator between those concepts, we may afterwards have good controls. And the problem in the control right now, the problem is step 3, may come because the step 1 is not finished yet, and we need a bit more work on extracting concept and formulating the correct phenomenology. So I'm going to finish in a few minutes, promise it's going to be short, on what I mean by when I say incomplete representation assumptions. So here it's a VLM, so it's a vision language model. So it's a model that you can give him an image or a text and give you a common embedding for those things. And if you train a small encoder or concept extraction on top of it, you find this. As you can see, 2 big islands. Half of the concept are text only, half of the concept are image only. What does it mean? It means that we know those models are truly multimodal. They work. However, if you train a basic SE and the basic method on top of it, they don't find this kind of multimodal concept. They don't find really the juice. And by observing the geometry, which is a work we've done with Isabelle Papadimitriou and Chloe Su, what we found is like there is a specific geometry that this model implement. And when you respect this geometry, so we built, for example, an SE that respect the geometry, that have what we call a conditional orthogonality on the way you select concept, no need for the detail. Well, the result is that when you do that, you get the juice. So you get one concept that tells you I'm an image, one concept that tells you I'm a text, and all the rest are like truly multimodal concept. So by inspecting some phenomenon, by inspecting some aspect of the geometry, we are able to instantiate a method that respect them, and then you get like way better interpretation of your space. So say it otherwise again, go back to the same old problem of there is a potential infinite number of ways to recast your activation, to factorize your activation, to find the concept basis. And you need some good inductive bias. You need some little signal to nudge into the good direction, to nudge to a direction, to a solution that is more probable. Another example is Dino. What I was showing you here is some images that you extract the concept and you show the first 3 components of those tokens, the last layers. And as you can see, it form like highly nonlinear / potentially like bounded regions. And it's not only true for those images, you can find it in a lot of places where the model seems to be like interpolating between abstract archetypes, like interpolating between clusters. This has been found also by other groups and make us wonder like what is going on there, and because it doesn't resemble like what we would call like the linear representation hypothesis. It more resembles something where we have some points, so some abstract region in the space that means something, and the model is like slowly circulating the tokens and the concept between those different regions. And so one, for example, as research that we've done lately, and I will leave you on that, is going back to attention, going back to the original formulation QKV, sigma QKV, which is equal to AV, A being the row stochastic matrix of attention. And if you look at this, A being the row stochastic, then geometrically you are building a convex hull. So here you have the values of your attention, V1, V2, and V3. And because of the attention, you can only lie inside this convex hull of those 3 values. So this creates a geometry that suggests it's a little bit more different than the LRH and potentially a little bit more rich. Because as soon as you had multi-head attention, then those convex hull combine and form what we call a Minkowski sum. And those Minkowski sum are polytopes. So that suggests, if we just look at attention, that suggests that the pattern that we are probably looking for, the representation of the model is look more like a polytops than, so bounded polytop, not polyhedra, bounded polytop than just linear direction. And this has an implication, of course, for steering and how we should control the model. No longer direction, but going to a point. Here is like we go to a direction, and here we go to a point. As you can see, even on those really simple cases, the steering, the control is not at all the same. Voila. I would like to finish on my last slide on talking about Peter Gardenford, which is the one that inspired us, basically looking into this idea of convex hull. He's a really beautiful researcher in cognitive science. He's published this beautiful book on conceptual space, geometry of thought. And inside it, basically advocate for a potential good representation hypothesis in our brain using convex hull and convex regions. We have some preliminary results that point in that direction, but still, I think the problem is really open. So a recap is current extraction method or instance of dictionary learning. We just saw that with like NMF, SAE are just solving the exact same problem with different constraints. They are grounded in the similar hypothesis, in the same hypothesis, which is the linear representation hypothesis, LRH. This hypothesis has already, one could say we have already like some empirical success with this hypothesis, which suggests at least partial alignment. I would be surprised if this hypothesis was completely wrong. But sign remains that this hypothesis has also some limits, and the phenomenology that we are building on is probably incomplete. So to move forward, one question that I'm working on with some of my friends and colleagues is what's the phenomenology we are missing? And I would like to thank all my collaborators. I would not be there without them, and I've been super lucky enough to work with a lot of people across many years, 5 years now, and so I would like to thank them one more time. Thank you, everyone. And if you have any question, I'm here to answer.
So Sebastian is asking if can this concept-based method be used for identifying overfitting, and if so, can you leverage it to forget regularization during training or fine-tuning?
So a lot of question there. Could it be used to characterize or to detect overfitting? That's a good question. That's a good question. I haven't thought about it. I suspect indeed that the additional structure that we are seeing, okay, so the fact that we are not just packing features, the fact that we have some actual, I don't know, additional structure on top of the model, may be a sign of this non-overfitting, on the fact that the packing is maximally attained, and so the model has to do something else. So maybe there is something where, looking at the geometry and like, are we in the packing mode where we just pack a lot of facts on top of each other, or are we in the mode where we reach the limit of our capacity, and then we have to make some abstract concept or some abstract feature that summarize some of a different aspect. If we would have able, I mean, if we had access to this, if we were able to detect when we are packing and when we are merging stuff, I think that would be a potential good candidate for noticing this kind of overfitting. But yeah, I'm not completely sure. But that's a good question, actually.
I think that the other work you just started about detecting and measuring, getting metrics for specification and generalization, maybe together with the ability to understand whether a certain concept is at all a concept that the model utilized to overfit to a certain domain, like two those kind of metrics together could be interesting to get hints on overfitting.
Absolutely. Yeah, maybe also the generalization, I haven't thought about, but the generalization of a concept. If a concept appears one time, it's probably extremely specific. So yeah, we can also have this kind of original trade-off between specificity and generalization.
Yeah. And he's also asking, like, in case we know and we are able to detect, is there anything to do in order to regularize or to improve the overfitting on those specific cases?
Yeah, definitely. I mean, I would say the first part is the hardest, like noticing when we are overfitting. But then if you have access to some kind of concept that you know are not good, then in the concept basis, you just put them to 0. So you go activation, concept, activation. And while you are in the concept basis, you put them to 0. And so you reconstruct your activation without some specific information that you think or you're suspicious about. So like, let's say I'm suspicious about this concept. Activation, concept basis, removing it, going back to activations. That would be, yeah.
It's setting the weights to 0.
Exactly. Setting the, yeah.
There is another very interesting list of work lately. It goes around unlearning or forgetting. And they building, those skip nodes around certain kind of content. They do it mainly, for security kind of things and avoiding leakage of secure information. But together with concept learning, you might be able also to force the model to generalize or, to collapse into a better route you approve.
Absolutely. Yeah. We are working on it with one of the leading figure in learning, Eleni Trafiantalou at Google. So we just published a paper and a review at a big conference on this topic. Yes. And what we found is that there is, because of this geometry, so the geometry again is like not perfectly orthogonal. So when you have a direction of a concept, it slowly epsilon interfere with other, what we realize is like removing a concept has some kind of rebound effect. So some other concept get impacted by the one you just remove, and we are not sure like if it's an artifact again of this the geometry that we are dealing with, or if it's an artifact of the method themselves. So we are actually trying to study a little bit more on that topic. But yeah, I think that there is a lot to do in that direction too.
Interesting. Everyone here, if you have any more Q&A, feel free to submit them. You have a Q&A button just in the bottom of the screen. And we have Thomas here for just 3 more minutes, so taking advantage of that. Thomas, there is you had a part in the presentation you spoke about. You showed that the model tending to learn specific concept, and while you keep training it to how it moves from deeper layers to earlier layers in the model. And there is a different kind of works that I think they had a bit more focus about 5 years ago about mutual information theory in general within works, and they're showing a similar kind of phenomena.
Is it the work from TGB?
Well, I'm familiar with Naftali Tishby. Naftali Tishby used to teach in Israel. He used to be professor in the Hebrew University in Jerusalem. Yeah.
Yeah, he has done a work on that. It's pretty famous. What he was basically saying is like the closer you get to the final, the more the mutual information with the label is increasing, but the more it decreases with your original input. So you kind of have this kind of trade-off between the two. One thing that we realized we're doing this work was like mutual information and Shannon information is pretty weird when you think about it, especially when we study neural net. Why? Because if you take an image and you encrypt it, let's say with SHA-256, okay? So there exists a bijection, so a function that go back to your original image, okay? However, if you train your neural net on the encrypted image, it will never work. You will not work on ImageNet, for example. You cannot learn anything. So Shannon is telling you the information is there, 100%. It hasn't moved. The information hasn't moved at all. But the neural net is telling you, I cannot extract it. It's impossible. And why is this happening? Because Shannon is telling you if the information is here, but it doesn't tell you if it's easily extractable. And those are two different things. And there is a beautiful work that's called The New Information from Stanford people, a theory of usable information under computational constraints. One of my favorite paper. It's basically trying to rebuild Shannon theory from the ground up, and they managed to basically go back up to the mutual information with this idea of computational constraint. What information can I extract given a 1-layer, a 2-layer, a 3-layer, a 4-layer neural net? So basically, you found that a lot of the inequality, like the data processing inequality or all those kind of things, are becoming false in that regime where you don't have an infinite extractor, and you can redevelop an entire new, research based on like this kind of weird notion of information that is an information with computational constraint. And I think that this is how we started this paper, the paper with Catherine. And funnily enough, we found when I was looking into that Shannon had wrote I mean, in the paper, like the new information, not formalize it, but he was aware of this particular characteristic and thought that it would be interesting to extend his theory to this kind of stuff. So yeah, even way before everyone thought about it. So yeah, there is definitely a lot of to look at on that direction too.
Yeah, definitely. Fascinating subject. And I believe that, some of those metrics we're trying to understand around concept and their contribution and their risk and the stability, we might be able to achieve some, good intuitions and even maybe methods from those areas as well.
I agree.
Thomas, thank you so much. It was amazing talk. I enjoyed it a lot. I'm sure that everyone that joined as well. We're gonna run those webinar every month, and we'll publish our next speaker in the next few days. So just stay tuned. And again, thank you a lot, Thomas.
Thank you very much. I wish you a really good day. Bye bye.